In this video, we'll get into some of the definitions that we're going to use to talk about differential equations over the course of this semester. So as we will see, and as we keep going forward, not all differential equations are easy or even possible to solve by hand. A lot of them need to fall back on these numerical methods to solve them, which we'll get to eventually. In order to facilitate knowing which can and can't be solved by hand, we need to figure out ways to classify these differential equations so we can tell what sort of class they fall into and know how we want to approach trying to solve them if we can, or giving up and going to numerical methods if that's the only way forward. Let's start from the beginning. What is a differential equation? Well, a differential equation is an equation involving an unknown function and its derivatives. For this, we'll call y the unknown function, but it could be any letter you want to use. So it's an equation involving an unknown function that we'll call y and its derivatives. We call this an ordinary differential equation if y has only one independent variable, and so all the derivatives in the equation are normal derivatives. This is in contrast to a partial differential equation, which is if y has more than one independent variable, and so the derivatives that are all there are going to be partial derivatives, not normal Calc 1 derivatives. If you want to abbreviate these as is normally done, ordinary differential equations are only called ODEs, hence the name of this course, and partials are called PDEs. We won't see much, if anything, from PDEs in this class. That would be a future class like 421 if you take that. Now, one other definition here is that of a system of differential equations. So a system of differential equations is when you have multiple things that are changing and are dependent on each other for how they change. So a system of differential equations, which could be either ordinary or partial, it doesn't really matter, has multiple dependent variables, and the rates of change of those dependent variables can be dependent on themselves or the other unknown function in the system. Or another approach is that a system is one where I have multiple unknown functions I'm trying to deal with as opposed to just one that I have in a single differential equation. Now, that's one level of classification, whether it's an ODE, a PDE, or a system. However, that's not really enough to tell us if we can solve something or not. We need some more terms to be able to classify them beyond that. Next term we have is order. So the order of a differential equation is the highest derivative, or the most number of derivatives that shows up at any point in the equation. For example, if I have an unknown function y of t that I know solves the following differential equation, this I have no idea how to solve. But I can figure out what the order is. The order is the highest derivative that appears. In this case, it is the third derivative over here on this first term. Even though this is a derivative raised to a power here, this is the second derivative cubed, it is not a sixth derivative. So the highest derivative that appears is this third derivative, so this is a third order equation. And it is an ordinary differential equation because y only has one independent variable, only depends on one thing. A note for this in terms of how we're going to write and display all of our equations for this class, we will always assume that we can write the highest order derivative by itself on one side of the equation. For this last example, it's not really a problem. I could just take all of these terms and move them to the other side, and that would be totally fine. I would get the third derivative term equals other stuff. That's great, that's fine. The main reason we had this for equations like the following: if I had a y of t squared plus a dy dt squared equals 1, this is a first order equation, and I need to be able to solve out for this on one side of the equation. So this wouldn't really work in our context as something we want to try to solve, because if I were to solve out for that, I'll get a plus minus sign. Right? Solving this out gets me, and I don't know if I want plus or minus here. Picking plus or minus is defining what the equation is. So this won't have the same properties that we are expecting of all of our equations as one of the choices of plus or minus here. It's a technicality, won't really come up that often, but if you try to think about the different types of functions that will solve this equation, you'll run into problems with counting solutions that you don't run into if you pick a plus or minus on this one. And the last term I want to talk about at this point is the idea of a linear differential equation. These are really the easy kind of equations. These are ones that we like because they're easier to solve. We have better ideas of how to actually handle things if they are linear. So we say differential equation is linear if it is linear in the unknown function and all of its derivatives. So what does that mean? Well, that means that in the equation, the function derivatives show up only raised to the first power. So they're not squared, they're not cubed, they're not square rooted, none of that stuff. So y and derivatives are only raised to the first power. They are not multiplied by each other, and they aren't inside of functions like exponentials or trig. Otherwise, we say the equation is nonlinear. It seems like those are pretty strict constraints, and you'd be right. They are really strict, and that's why we get so much benefit out of being able to solve them if we know it's linear, because we know it has a certain set of nice properties that'll help us in solving the equation. Some examples of this real quick. Something like this. This is a second order linear ordinary differential equations. Notice that all of these linear constraints only depend on y, the unknown function, and not t. So t can be in exponentials here. That's great. T can be in trig functions. Great. In the denominator. Also great. But the unknown function y and its derivatives must all show up by themselves to the first power with nothing attached to them in terms of y. Something like what we did for the previous example. This here is nonlinear, and it's nonlinear for two reasons. It's nonlinear because of this cubic term here. It's a function of y that is cubed, so this makes it nonlinear. But also, the y times dy dt makes it nonlinear because they cannot be multiplied by each other. Either the t is totally fine, but the y dy dt term and the cubic term here make it nonlinear. Let's look at the examples from earlier as well, the physical examples. We had the mixed reactor here. This is a first order equation because I only see one derivative, and it's nonlinear because of the c squared term here. Otherwise it's fine, but that makes it nonlinear. And it's ordinary because these are ordinary derivatives, and c only depends on t. The second example, this is a second order equation, and the easiest way to see that might be to expand out that product rule. So if I do out that product rule, I will see a 1 over r times derivative falls on r plus a 1 over r derivative falls in the du dr equals alpha, or rearranging terms, second derivative plus 1 over r du dr equals alpha. So second order because the second derivative shows up and it's the highest derivative that shows up. It's also linear because I have a u term here by itself, u term here by itself. It's multiplied by 1 over r, but it's not multiplied by u, and that's what would destroy this process, and that's a constant, so it's fine. For the last example, we have this bioreactor. This is a two-component system because I have two unknown functions here. It is first order, and it's nonlinear. It might look linear at first, but because this mu depends in a strange way on x2, it's not actually a linear equation. If this mu was a constant, then this would in fact be a linear system here. But since mu depends on x2, it's nonlinear. So that's the idea of how we can go about classifying differential equations. Things like whether they're an ODE, a PD, or a system, what order they are, and whether they're linear or nonlinear are important facts to know before you try to approach how you might try to solve these differential equations, as those classifications will give you techniques you can use to try to handle it.